So it's all in the name, quadratic number patterns. I'm sure you all know what a quadratic function is, right? Yes, 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 it's a parabola. And what signifies that we're dealing with parabolas? We always deal with x to the power of 2, right? So a quadratic number pattern is exactly the same as working with a parabola, where the terms in the number pattern, the values given are the y values and the term numbers are the x values. And just as a parabola's formula is y equals ax squared plus bx plus c, a quadratic number pattern's general formula is tn equals an squared plus bn plus c. N is your term number. Jot that down as I haven't given it in this slide. And Tn as a whole is like a y value for a function. It is the term value at a specific term number. Right, so let's, how do you know whether or not something is a quadratic number pattern? Or remember that another word for number pattern is sequence. If we're dealing with a quadratic sequence, you must look out for a constant second difference, alrighty? So in any number pattern, you should look at the first difference and then look at the difference between the first differences. How do we do that? Let me demonstrate by means of an example. So, determine the general term for this number pattern. Right, so in other words, we need to find values that we can replace a, b, and c with in this general formula up above. So, let's have a look at our first differences. The way to find your first difference, also write this down if you need to because I haven't typed up the formula. It's T2 minus T1. Or my brain likes to see it as, what did I add to 2 to generate the number 6? And that's much easier for me to say, aha, I added a number 4. Or what did I add to number 6 to generate number 14? What is T3 minus T2? Aha, I added the number 8. Last but not least, to get from 14 to 26, T4 minus T3 equals 12. So these numbers right here are not constant. In other words, the same number doesn't repeat itself. So this is not a linear number pattern, which we will deal with in the next video. Right now, these numbers differ by a certain number. The first differences are not constant. However, to get from 4 to 8, you add 4. To get from 8 to 12, you add 4 again. And so we have a row of a second difference which repeats itself. So the second difference is constant. So therefore we can conclude we are on the right track. This is indeed a quadratic number pattern. Now how are we going to find values for A, B, and C? Well. We remember 3 little formulae. Please memorize these. 2a is always equal to your second difference. Then once you solve for a, you can replace this a in the general formula with that value. Then the next little formula, we use that a that we found along with and multiply it by 3 and add a b. So 3a plus b equals the first term of your first differences. The first term of your first differences is 4. 3a plus b equals 4. We have a value for a, so we can find the value for b. Last mini formula that you need to memorize is a plus b plus c. Now the previous 2 mini formulae allowed us to find a and b. We substitute those respective values into this formula and we equate it to the first term of the given sequence. Note I'm going to alternate between saying number pattern and sequence. I need you to realize that those are synonymous. A sequence and a number pattern is the exact same thing. A little later on we're going to learn about a series, which is not the same as a number pattern or sequence. although very similar. Right, so here we can finally substitute in values for A and B, and ta-da, we will get C. So I'm not going to waste any time. I'm going to actually find the specific values. Once you have all three, you can substitute it into the formula, and voila, look at all those lovely 2's. This is a 2n squared minus 2n plus 2. If I would like you to also always challenge yourself by imagining this as a parabola. Would this be a happy parabola or a sad parabola? A happy one, right? Because A gave us a positive value. What would the y-intercept of this parabola be? It would be the constant at the end. Would this parabola's turning points lie on the left-hand side or the right-hand side of the y-axis? Well, substitute negative 2 into minus b over 2a to see the sign of the x value of the turning points. I know I'm digressing here a little bit, but I just think it's so fascinating how a quadratic number pattern is merely a parabola. So if you're confident with functions, you should be A-okay in this section. Let's see if we can expand on this. So which term in the sequence has a value of 422? We have generated the general formula for this, and now they're asking us which term. So basically we need to find n. So if we are given a value, we replace the entire left-hand side of this equal sign. We replace the tn as a whole with the number 422. There's a highest common factor of 2, so I'm dividing every single term by 2. I'm kicking my 211 over, and here you can fake factorize by whipping out your silver calculator and hitting that equation mode, or you can use your quadratic formula, minus b plus minus square root of b squared minus 4ac all over 2a, whatever. Or if you are incredibly impressive with your factorizing and can create those brackets yourself, good for you, as long as you boil down to n equals 15 or n equals negative 14. However, can n be a negative number? Can you have a term in a sequence being negative? That's like saying you standing in a queue at the bank and you are number negative 14 in the queue. Not possible. So for number patterns, n is always greater than 0. All right, it's a positive number always. So that's that. N is 15. The 15th term in this number pattern will have that big value of 422. Beautiful. Well done.